In this video, we're going to have a look at a non-homogeneous second-order differential equation. So the general solution, actually even before we get into that, how we know this is non-homogeneous is the right-hand side is actually not equal to 0. Now in this case, the general solution is the sum of the complementary function and the particular integral function. Let's take this step by step and start by finding the complementary function. In order to find this, we need to form an auxiliary equation where we replace dy dx with m, in which case d squared y over dx squared is m squared. The middle term now becomes minus 6m, and this 8y just becomes a constant of plus 8. You make that equal to 0 and you solve this equation for m. I'm actually just going to increase the thickness of the pen. If we factorize this, sorry, I don't know, I'm talking in slow motion, but it can factorize to m minus 4, m minus 2. You can make all that equal to 0, in which case you get two different solutions. Either when the first bracket equals 0, m equals 4, or m equals 2. Now, when there's two distinct real roots, we say the complementary function is in the form ae to the power of m1x. m1 just means one of the values of m, plus be to the power of m2x, where m2 is the other value of m. A and b are just constants that you are only able to find if it tells you information that you can substitute into it to find. But this question doesn't tell you, for example, when x is this, y is this, and dy dx is this. That's a particular solution, and I'll make a separate video going through that later. Now that we've got these values of m, we can say the complementary function is ae to the power of one of the values of m, it doesn't matter which one you choose first, plus be to the power of the other value of m, x. We now need to find the particular integral. So how do we go about doing that? Well, whenever the right-hand side is a power of the exponential, what we want to try for the particular integral is any constant c, e, and then we want to make the power match the power on the right hand side. The reason we want to make the powers match is because what we're saying is that when you differentiate y twice, when you differentiate it again, and then you add 8 lots of y onto whatever y is, that's going to equal e to the power of 3x. If we look at our current expression, no matter how many times we differentiate this first term, it's always going to have a power of 2x, and the second term, no matter how many times we differentiate it'll always have a power of 4x. These terms can never combine into this equation to give a power of 3x, and that's why we introduce a particular integral. Now for that particular integral, so I'm going to write here, try y pi equals ce to the power of 3x, we need to find d squared over dx squared and dy dx. dy dx is what you get when you differentiate y, so that becomes 3c e to the 3x. You do have to have prior knowledge, by the way, that e to the 3x would just differentiate to 3e to the 3x. Moving on, the second differential is, well, 3 times 3c is 9c, so it becomes 9c e to the 3x. And substituting that into this equation, the left hand side that is, we get y double prime, which is 9c e to the power of 3x, minus 6 times all of this, which is, well, 6 times 3c is 18, so minus 18c e to the power of 3x, and then plus 8 lots of y, which is plus 8c lots of e to the 3x, is all equal to the right hand side e to the 3x. Because all of these terms just have e to the 3x, we can look at the coefficients of e to the 3x. 9c take away 18c is minus 9c, plus another 8c is minus 1c. We can say minus 1c is equal to, well, the coefficient of e to the 3x here would be 1, in which case c would just be equal to minus 1. Now that we actually know the value of c, we can write down and denote that the particular integral is just minus 1 e to the power of positive 3x. Finally, we can form the expression of the general solution because we know the general solution is a complementary function, which is this whole function here that we introduced, ae to the 2x plus be to the power of 4x plus the particular integral function, which is just minus e to the power of 3x. And that's the general solution. Again, we could have found the particular solution only if it gave us specific values to substitute into this, but it hasn't really given that here. Thanks for watching the video, I hope it helped. If you have any tutoring inquiries for A-Level Further Maths, be sure to hit my website up at www.excellineducation.co.uk.